Hello, this is Matt Dean, and today we're going to work some simple harmonic motion practice problems. We'll begin with problem number 1. If the length of a pendulum is increased by a factor of 4, by how much does the period of the pendulum increase or decrease? Be sure to indicate whether the change is an increase or a decrease. When you're working with a simple pendulum, the equation for the period is T equals 2 pi times the square root of L over G, where L is the length of the pendulum and G is the acceleration due to gravity. So we're saying we increase L by a factor of 4. Well, since that's under the radical, we take the square root of 4, and the period is going to increase by a factor of 2. So our answer on this one is going to be C. All right, so now we're going to look at problem 2. A mass of 0.35 kilograms is connected to a massless spring with a force spring constant of 70 newtons per meter. The system oscillates on a frictionless horizontal surface. The amplitude, remember amplitude is the maximum displacement away from equilibrium, is 4 centimeters. What is the total amount of mechanical energy in the system? All right, here's what we've got to think of. So we have this horizontal surface. Here's our spring. And let's say right now this thing is at equilibrium. So it's going to oscillate back and forth. So when it's at its maximum oscillation distance or its maximum amplitude, let's say somewhere over here, it stops. At this point, at maximum amplitude, all of the mechanical energy is elastic potential energy. So if we can calculate the amount of elastic potential energy either at maximum stretch or at maximum compression, we can calculate the total amount of mechanical energy, because at those points, it's all elastic potential. In between those 2 points, we also have some kinetic mixed in. So let's do that. So we're going to use the equation US equals 1/2 kx squared. So in this case, it's going to be 1/2 times k, our spring constant, times x squared. Now, since the spring constant is in newtons per meter, we need to put our x, our amplitude, in meters. So 4 centimeters is going to be 0.04 meters. Can't forget to square that. So if we do the math here, we multiply that out, we end up with a amount of elastic potential energy, or in this case, all of the mechanical energy of the system, equal to 0.056 joules, which would be answer A in this case. All right, so practice problem 3. An astronaut wants to determine the acceleration due to gravity on a planet other than Earth by means of a pendulum. He observes that a 2-meter-long pendulum has a period of 3.2 seconds. What is the value of the acceleration due to gravity on this planet? Well, as you can see up here, here's the equation for the period of a pendulum. It involves both the length of the pendulum and the acceleration due to gravity. So if we take that equation and we solve it out for G, we end up with this. So again, this equation on the bottom is simply this equation rearranged for G. So then we plug in what we know. So G is going to be equal to 4 pi squared times L, the length of the pendulum, in this case 2 meters, over the period squared. So it's 3.2 seconds squared. If we do the math in this case, we end up with B, 7.7 meters per second squared. All right, on to practice problem 4. A 0.5 kilogram mass is attached to a vertical spring, and the spring stretches 0.125 meters. What is the value of the spring constant for this spring? So in this problem, we're going to use Hooke's law. Now remember, Hooke's law is F equals negative kx. We're trying to find the spring constant, so we're going to solve this out for k. So negative k is going to be equal to F divided by x. The force here is going to be the weight of the object. So it's going to be 0.5 kilograms. We're going to use 10 for the acceleration due to gravity. So 0.5 times 10. So we end up with 5 newtons. Over the displacement, which is 0.125, but it's 0.125 down. So it's going to be negative 0.125 meters. We divide that out, and we end up with 40 newtons per meter. So our answer on practice problem 4 should be B. On first glance, practice problem 5 looks like the same problem as number 4. and it does involve a lot of the same elements. But in this case, we're going to take that same spring and mass, we're going to put them on a frictionless horizontal surface, and we're going to set that block into simple harmonic motion, and we want to know the period of the oscillations. Remember that when we have a mass on a spring, the period for mass on a spring is 2 pi times the square root of m, which is mass, over k, the spring constant. So T equals 2 pi times the square root of the mass, which is 0.5 kilograms. And we just found in practice problem 4 that the spring constant for this particular spring was 40 newtons per meter. So if we do the math on this one, we end up with 0.702 seconds as the period. All right, so practice problem 6. A simple pendulum of length L and mass M is placed at an angle theta away from the vertical and to the right. So let's say that the pendulum started out here, straight up and down, and then we pulled it to the right, an angle of theta. We want to know, how can we find the tension in the pendulum cord? So when you're doing these kinds of pendulum problems, the first thing you want to do is go to your pendulum, and you want to draw in a vector that represents the weight. You then want to break that weight vector down into components. One of those components is going to act along the string, and that's going to be the tension. And one of those components is going to point back toward the equilibrium position, and that's going to be the restoring force. Remember, this angle right here is also going to be theta. We know the weight. So if we solve this out for tension, we can say that the cosine of our angle theta right here is going to be equal to the adjacent side, which is the tension, over the hypotenuse, which is the weight. Solve that out for tension. Tension is going to be equal to weight times cosine theta. Well, if you look, that's not listed as one of our answer choices, but remember that weight is simply mass times acceleration due to gravity. So our answer on this one is going to be answer B, and that's going to allow us to find the tension in the pendulum cord. All right, practice problem 7 again looks very much like practice problem 6. But in this case, we want to know which of the following represents the amount of gravitational potential energy stored in the pendulum bob when the pendulum is at angle theta. So let's say our pendulum started out here, vertical, and then we displaced it to the right, angle theta. As we were moving it to the right, we were also lifting it. And since it was being lifted, it is gaining gravitational potential energy. We know that gravitational potential energy can be calculated using mass times acceleration due to gravity times height. So we need to know how high we lifted it. To do that, we're going to come to our pendulum bob here, and we're going to draw over a horizontal, like so. We know that this length is the length of the string. We can calculate the length between here and here. And we can do that using cosine. So we're going to say the cosine of our angle theta is equal to the adjacent side, L. Nope, sorry. The adjacent side, which we're looking for, let's just call that X for right now, over the hypotenuse, L. So X is going to be equal to L cosine theta. Well, now this cable here was the entire length of the string. And what we ended up doing, though, is now it's been lifted this much. So to find that, we're simply going to take the total length of the string, L, minus this piece of that string length, L cosine theta. So the height that it's been lifted to is going to be L minus L cosine theta. And then we're going to get the gravitational potential energy, we're going to multiply that quantity times mg. So the gravitational potential energy is going to be mg times L minus L cosine theta. And if you look at our answer choices, answer B is going to be the correct answer here. All right, practice problem 8 is very much like practice problem 2. We have a mass on a massless spring, force constant of 70 newtons per meter. It's oscillating on a horizontal frictionless surface. And the amplitude, the maximum displacement away from equilibrium, is 6 centimeters. We want to know the total amount of mechanical energy of the mass spring system. Remember that when the oscillator is at its maximum displacement, either compression or stretch, all of the mechanical energy is going to be elastic potential energy. In between those 2 points, there's both kinetic and elastic potential. But at the amplitude, all of the mechanical energy is elastic potential, which we can calculate using 1/2 kx squared. So that's going to be 1/2 times 70 newtons per meter. Remember, since this is in newtons per meter, our displacement also needs to be in meters. So we're going to say 0.06 meters. Don't forget to square that. So if we do the math, we end up with 0.126 joules as our answer here. So it looks like answer D is going to be the correct answer for practice problem number 8. All right, practice problem 9 looks very much like practice problem 8. This time, though, it says the system oscillates on a frictionless horizontal surface, same amplitude as we had in practice problem 8, 6 centimeters. We want to know what is the speed of the oscillating mass when it is located 3 centimeters from the equilibrium point. Now, some of you would be tempted to take that total mechanical energy that we calculated in problem 9, half it, and set that equal to the kinetic energy equation, 1/2 mv squared. But we can't do that because the spring constant varies with the displacement. So this oscillator is not uniformly accelerating. So here's how we would work a problem like this. We know how much total mechanical energy there is in the system. We're assuming that's not changing because there's no friction. We need to calculate how much elastic potential energy there is in the spring system at the 3 centimeter displacement. So we're going to say 1/2 times K times x squared. And that gives us an elastic potential energy of 0.0315 joules. The rest of the system's mechanical energy at that point must be kinetic. So we need to subtract this quantity from the total mechanical energy up here. So 0.126 minus 0.0315. And that tells us that there's a kinetic energy of 0.0945 joules. Now we're going to take this quantity and we're going to set it equal to 1/2 mv squared. So we're going to say 0.0945 joules equals 1/2 times the mass, which we know, 0.5 kilograms, times v squared. So now we simply solve this for v squared, solve for v rather, and we end up with 0.61 meters per second once we solve that out for v. So answer A is what we're looking for on practice problem number 9. All right, practice problem 10. We have an object attached to a horizontal spring. It's put in oscillatory motion, and a position sensor is used to record the displacement from equilibrium as a function of time. The obtained data is graphed in the graph below. The total distance traveled by the object between t equals 5 seconds and t equals 9 seconds is. So we go to our graph. Here's 5 seconds. 9 seconds would be right there. So notice between 5 seconds and 6 seconds, the object travels 25 centimeters rather. Between 6 seconds and 7 seconds, travels an additional 25 meters. Between 7 and 8, an additional 25. And then finally, between 8 and 9, another 25. So 4 25s is going to give us 100 meters of total displacement. This thing travels one complete cycle between 5 and 9 seconds. But our answer here is 100 centimeters. All right, again, this looks kind of like the same problem from number 10, but this time we want to know the frequency of the oscillation. Now, just a minute ago, we were looking between 5 seconds and 9 seconds. And we said between 5 seconds and 9 seconds, this thing completes one cycle. It goes all the way up to its peak and comes all the way back to its lowest point and then starts over. So between 5 and 9 seconds, that's one period. and that's 4 seconds. So the period here is 4 seconds. Remember that frequency is equal to 1 over period. So our answer here is going to be 1 over 4, 1/4, or 0.25. We measure frequency in cycles per second, in this case oscillations per second, or hertz. So our answer here is B. So in this problem, we want to find the speed of the object at t equals 7 seconds. So we're looking for the speed at a particular time. We could think of that as an instantaneous speed. Or we've been talking about instantaneous velocities, but here we're not concerned about the direction. But if we want to find we have a graph of distance or displacement against time, and we want to find an instantaneous speed or instantaneous velocity, we go to that point on the graph, so 7 seconds. And you remember the slope of the tangent line at that point. So in this case, we're looking at essentially answer B is our correct answer here. Sorry, I picked the wrong choice there. Answer C, the slope of the tangent line to the curve at 7 seconds. If you want to know an instantaneous speed or velocity, and you have a displacement or distance versus time graph, you find the slope of the tangent line to the curve at that point. All right, so practice problem 13. A 5 kilogram mass at position A, so we'll say this is position A, is in contact with an uncompressed vertical spring with a spring constant of 500 newtons per meter. So the spring hasn't compressed any yet, which means at position A, the system has gravitational potential energy. Then the spring is frictionless. It's initially 60 centimeters above the ground. The block is slowly lowered from a rest position at A to rest position at B. And notice it changes by a height of x, a total displacement of 20 centimeters. Which of the following describes the change in the mechanical energy of the block, spring, or system as a result of the block being lowered? So we know as the block goes down, the amount of gravitational potential energy goes down. But as the block goes down, the amount of elastic potential energy goes up. And it turns out the negative change in gravitational potential energy is the same as the positive change in the elastic potential energy. So essentially what we're saying here is because there's no friction, mechanical energy is conserved. The mechanical energy of the system doesn't change. So we're looking at answer D as the correct answer. We could calculate this using these equations, but theoretically, I think this makes sense. All right, so on to practice problem 14. Here we have a 0.4 kilogram mass oscillating horizontally at the end of an ideal spring, again, which means no friction. We know the K for the spring, 60 newtons per meter. If the amplitude of the spring's oscillations is 0.8 meters and the maximum velocity of the mass is 9.8 meters per second, what is the total mechanical energy of the system? Remember, mechanical energy is equal to the kinetic energy plus the potential energy. So there's two ways we could calculate this. At its maximum velocity, we know that it has maximum kinetic energy, and essentially all the mechanical energy is kinetic. That maximum velocity happens when the displacement is zero. It happens at the equilibrium position. So we could use K equals 1/2 mv squared. We know the mass of the object, 0.4 kilograms. And we know the maximum speed is 9.8 meters per second. We've got to square that. If we do the math, we end up with 19.2 joules. And that's at the equilibrium position because that's where the maximum velocity takes place. Now, also remember, we could calculate this another way. At the amplitude, which is the maximum displacement away from equilibrium, whether we're talking about the compression or stretching of the spring, all of the mechanical energy is in the form of elastic potential energy. So we could use 1/2 kx squared. Our K is 60. Our x at maximum amplitude is 0.8. And if we do the math on this, we also come up with 19.2 joules as our answer. So it's looking like answer D on problem number 14. All right, so on number 14, while the object continues to oscillate, the maximum speed of the mass decreases over time. Which of the following accounts for the decrease in the object's maximum speed? So if the speed is maximum speed is decreasing, that means that there's some mechanical energy that's being lost. And it's not in the spring, it's being lost to the environment, to the surroundings. So the only answer here that makes any sense for number 15 is D. The amount of mechanical energy of the system is decreasing, probably due to friction. So in this case, the spring would not be an ideal spring. All right, practice problem 16. So we have a figure on the right that has a bar with a spring around it and a 0.2 kilogram block with a hole in the middle on the top of the spring. A small horizontal rope is attached to the block and the wall. When the block is oscillating at 10 hertz, we get a standing wave. What is the value of the spring constant of the spring? This sounds like a complicated problem, but really the only thing you need to work this problem is the period is equal to 2 pi times the square root of m over k. We need to solve this out for k. So when we do, k is going to be equal to m over period divided by 2 pi squared. All right, so we need to chug what we know. So K is going to be equal to the mass, 0.2 kilograms, divided by the period. Now we're given the frequency. Remember that period equals 1 over frequency. So if the frequency is 10 hertz, the period is going to be 0.1 seconds. So we're going to have 0.20 kilograms over 0.1 seconds over 2 pi quantity. The whole quantity is squared. So when we do the math here, we end up with an answer of K is equal to 789 newtons per meter. A question almost exactly like this has been on 2 out of the last 3 released mock exams. So this is something you need to make sure you know how to do. All right, this question also came off of 2 of the last 3 mock exams. We want to find the speed of the wave. Now, this is something you may not know how to do just yet. When you're talking with waves, there's an important equation. The speed of the wave is equal to the wavelength times the frequency. Well, we're looking for speed. We're given frequency, so we need to know the wavelength. The wavelength is the distance between any 2 adjacent points, same points on 2 adjacent waves. So it could be between 2 adjacent troughs or 2 adjacent crests. So what I'm saying is that the answer we're looking for here, the wavelength, can be expressed as C. So answer C on problem number 17. All right, practice problem 18, we're back to pendulums again. This time we have a pendulum which reaches a maximum height of y above the equilibrium position as it swings. If friction and air resistance are negligible, which of the following is true about the energy of the earth pendulum system as the pendulum swings? This is one of those choose to answer multiple choice questions. So let's just go through the choices one at a time. Kinetic energy is lost with each oscillation during the conversion to elastic potential energy. The kinetic energy might be converted to elastic potential energy, but we'll get it back if mechanical energy is conserved. So answer A does not look like a valid choice to me. Answer B, the gravitational potential energy is at a maximum when the pendulum is at its maximum height. Well, remember that gravitational potential energy is equal to mgh, which means that it would be at a maximum when the height is at a maximum. So B looks like a good choice. C, the total mechanical energy of the system is constant throughout the pendulum's motion. Well, the problem stem tells us that we're ignoring friction and air resistance. In those cases, typically mechanical energy is conserved. Remember, mechanical energy is the sum of the kinetic and the potential. So answer C looks like a valid answer. Finally, the kinetic energy is at a minimum when the pendulum is somewhere between its lowest and highest positions. Well, the kinetic energy is at a minimum at the highest position. It's at a maximum at the lowest position. So answer D is not correct. So practice problem 18, we're looking at choices B and C as our correct answers. All right, so practice problem 19. We've got a graph that illustrates the force exerted by a spring as a function of the displacement of the spring. We take a block of mass 0.25 on a frictionless table. We push it against the spring, which is fastened to the wall, and we compress the spring by 2 centimeters. The block is released. With what speed will the block leave the spring? Here's what we can do. We can use this graph, first of all, to find the spring constant. Because remember, Hooke's law is F equals negative kx. Solve for k. So what we can see is that k, negative k at least, is the F over x. Well, our y-axis is F, and our x-axis is x. So we need to divide F by x. So essentially we can find the slope of this line. So take any 2 points on the graph, find the slope between them. And when you do that, a slope of this line turns out to be 500 newtons per meter. So that's our K. Next, when we compress it at 2 centimeters, that's going to be our maximum compression in this problem. So all the energy that we have at that point is going to be elastic potential. So we can calculate the elastic potential energy, 1/2 times K times x squared. Our x is going to be 0.02 meters. We need to square that. And when we do, we end up with an elastic potential energy of 0.1 joules. So then we let this thing go. The spring is going to stretch all the way out, and at that point, all of the elastic potential energy is kinetic, and the box will then move away from the spring. So at the point when the box leaves the spring, all of this elastic potential energy is going to be kinetic. So we're going to set that equal, the 0.1, equal to the equation for kinetic energy, which is 1/2 mass times velocity squared. And we're going to solve that out for V. And when we do the algebra and solve for V, we end up with a speed of 0.89 meters per second. So we're looking at answer A as our correct answer on problem number 19. All right, for our last multiple choice problem, number 20, we have a pendulum with a small bob oscillating in simple harmonic motion. The bob is then replaced with a new one that has the same size but a much greater density. That means it has more mass. The new bob is set in simple harmonic motion at the same angle as the original pendulum bob. How do the period, the maximum kinetic energy, and the maximum acceleration of the new bob compare to the original bob? Well, for period, we know that the period of a pendulum can be calculated 2 pi times the square root of L over G. And I hope you see that the period isn't dependent on the mass, which is what we're really changing in this problem. So it doesn't change. Well, that tells us our answer either has to be C or D, because the period doesn't change. Well, the mass increases. We know that kinetic energy is 1/2 mv squared. Well, since there's more mass, there's going to be a larger amount of kinetic energy, assuming the speed is the same. So kinetic energy should be larger. So it's looking like D is probably going to be our answer. Let's check the acceleration. So when we increase the mass, we're going to increase the inertia, make it harder to accelerate. But also when we increase the mass, we're going to increase the restoring force. Those two changes are going to be balanced out, and the maximum acceleration of our bob is going to be the same in either situation. So for practice problem number 20, answer choice D looks like a good answer. right, so now we're ready to look at the free response question for our simple harmonic motion practice problems. So we have a 3 kilogram object subject to a restoring force F. It's undergoing simple harmonic motion with a small amplitude. The potential energy of the object as a function of distance from its equilibrium position is shown above in the graph. This particular object has a total energy, and that's mechanical energy, of 0.4 joules. What is the object's potential energy when its displacement is plus 4 from the equilibrium position? All right, so we go over to about plus 4 from the equilibrium position, about right here. And then we follow that over to our y-axis, which is for potential energy. And that gives us about 0.05 joules at A. Now B, what is the farthest the object moves along the x-axis in the positive direction? Now some of you are going to be tempted to just see where the graph seems to end, somewhere around 13. You're going to write down 13. But remember, the total mechanical energy of the system can't exceed what we started with, which is 0.4. At that maximum displacement, all of that mechanical energy is going to be elastic potential energy. So what we need to do is we need to go up to 0.4 and go over. And what we see is that cuts the graph at about 10 centimeters. So they've just extrapolated our line on past that. Essentially, this thing is going to oscillate back and forth between positive 10 and negative 10. So our answer on this one should be about 10 centimeters. That's for B. C, determine the object's kinetic energy when its displacement is -7. So let's go to -7, which would put us about right in here. Go up and cut the graph. So at -7, the amount of potential energy is about 0.2. Remember that mechanical energy is potential plus kinetic. We had 0.4 joules of mechanical energy. At -7, 0.2 or so of those joules is potential, which means the rest has to be kinetic. So we're saying at -7, we've got about 0.2 joules of kinetic energy. And that's our answer on C, 0.2 joules. Finally, on D, we want to know the object's speed at x equals 0. Well, at x equals 0, there's no potential energy, which means all of the energy has to be kinetic. So all 0.4 joules are kinetic. So we're going to say K equals 1/2 mv squared. We're going to solve that out for velocity. So we're going to multiply both sides by 2. Cancel that out. We're going to divide both sides by mass. And then we're going to take the square root of both sides to solve for V. So V equals the square root of 2K over M. So in this case, we're going to have 2 times the kinetic energy. All of the energy is kinetic at that lowest point, over the mass of our object, which was 3 kilograms. We'll take the square root of that whole quantity. So 2 times 0.4 divided by 3. Take the square root of that whole quantity, and we end up with a speed of essentially 0.5 with 1 sig fig. We're looking here at, 1 sig fig is really what we need. 0.516 is what my calculator says, but we were only dealing with 1 sig fig. So 0.5 meters per second is what we're looking at on D. We have one more part, and that's E. So E says, suppose the object undergoes this motion because it's a bob of a simple pendulum as shown. If the object breaks loose from the string at the instant the pendulum reaches its lowest point and hits the ground at point P, what is the horizontal distance that it travels? All right, so to work this problem, first of all, we need to know the speed at this point. And we calculated in part D that the speed of the object when it reaches this point is about 0.516 meters per second. We rounded it off to 0.5 in part D. The string breaks. This object is going to start to move out at a right angle to the string. Well, it's got to fall 0.5 meters before it reaches the ground. This is a projectile problem. We know that the horizontal speed of a projectile doesn't change when we ignore things like air drag. But what does change is the vertical speed. So vertically, let's set up an equation and let's use the vertical distance to figure out how long it's going to take that object to drop the 0.5 meters. So we're going to use the kinematic equation delta y equals VOT plus 1/2 AT squared. Delta y is going to be our negative 0.5 meters. It's negative because it's falling. The VO is our initial vertical velocity. At this point, this object isn't moving vertically, it's moving horizontally. So our initial vertical velocity is 0 plus 1/2 times A. We're going to use acceleration due to gravity. We're just going to use negative 10 meters per second square times t squared. We're going to solve this out for t. And when we do, we end up with t equals 0.316 seconds. So to fall 0.5 meters, it takes the object 0.316 seconds. For that entire 0.316 seconds, that object is moving horizontally at this speed, 0.516 meters per second. So to calculate the horizontal distance traveled, we're going to use delta x equals vt. This is going to be 0.516. This is going to be 0.316. Multiply those together, and we get a delta x of 0.163 meters. And since we were dealing with 1 sig fig in this problem, we're going to write delta x equals 0.2 meters. All right, that's it for our simple harmonic motion practice problems. Hope that helps.